Okay, guys, what's up? It's Mr. Fow here, and we're going to go over the 10 questions from the PowerPoint. So, okay, so the first of the problems deal with the mole and factor labeling, unit conversion, and things of that sort. All right, so here's our first problem. X-ray diffraction causes electrons to ionize away from an element. It takes 1,230 kilojoules to remove 1 mole of electrons. How much energy is required to move 1 electron in joules? Okay, so all we're doing here is just converting units. So we're starting with 1,230 kilojoules of energy, and that's per a mole of electrons. That's per 1 mole of electrons. And the goal here is to change kilojoules to joules and moles of electrons to 1 lone electron. All right. So if we want to change the top unit, all right, for every 1 kilojoule, there are 1,000 joules. The kilojoules will cancel out. So we're left with joules. That's good for the top unit. And then on the bottom, we need to go from moles of electrons to 1 electron. Well, for a mole of electrons or a mole of anything, there are 6.022 times 10 to the 23rd items. Okay, so now we can solve. So up top we have 1230 times 1,000 and divided by 6.022 times 10 to the 23rd. And we get 2.04 times 10 to the negative 18th joules for an electron. Okay, that's question 1. All right. Question 2. All right, so this is an empirical formula problem. All right, should have learned empirical formula last year in chem. So we have a compound that's 75% carbon by mass and 25% hydrogen by mass. What is the empirical formula for the compound? So since we're not given how much we have, we can just assume we have 100 grams, make life really, really easy. So if we have 100 grams and 75% is carbon, that means we have 75 grams of carbon. And same thing, if we have 25% of 100 grams is hydrogen, then that means 25 grams of hydrogen. Right. We want to convert these to moles. Carbon has a molar mass of 12 grams per mole. That's 6.25 moles. Down here, hydrogen. Hydrogen has a molar mass of 1 gram for 1 mole, and that's 25 moles. All right, and then to find the empirical formula, we need to just find out the mole ratio. So to find the mole ratio, just divide by the smallest number. It happens to be 6.25. That means there's a ratio of 1 to 4. So for every 1 carbon, we have 4 hydrogens. So again, we took our percentages. We were able to turn them into grams because we just made the assumption that we had 100 grams to moles, and then mole ratio. So divide the moles by themselves, and then you get your 2 numbers, and that's the mole ratio. All right, question 3. So this is all about just explanations of concepts based on the mole. So 2 balloons are at STP, which is standard temperature and pressure. We have balloon A is filled with neon and balloon B is filled with argon. So let's talk about the following questions. So which balloon occupies more space? So earlier we stated that any gas at STP will always occupy 22.4 liters if it's got 1 mole of it. Since we have I have to fix this question. 1 second. Sorry about that. I just realized that there was a mistake in the notes. I forgot to include pretty vital information to that problem. My bad. Definitely prone to doing that. Do that throughout the course of the year. Okay. Here's the vital piece of information. I forgot to tell you how much was in each balloon. Can't do the problem without that. So each are filled with 1 mole. Okay, so back to the first question. Because they're both filled with 1 mole, they both will occupy the same volume, 22.4 liters. So the first question is, they both occupy the same space. Which balloon has a larger mass? Because they both because they both have 1 mole inside, then we just look at the periodic table. We find out that argon has a larger molar mass. Therefore, argon will be the larger balloon with respect to mass. Excuse me. Excuse me. Yeah, sorry. Which balloon has more atoms inside of it? They're the same. They both have a mole. 1 mole is always 6.022 times 10 to the 23rd of anything. So in this case, it's atoms of neon in one balloon and atoms of argon in the other balloon. Same number of atoms in each balloon, so same. And then which balloon has the larger density? So here, we have to just kind of think back to what we know about density. So if you forgot, density is mass over volume. Well, when we looked at question 1, we said which balloon occupies more space, and the answer was they occupy the same space. So really, for this thing, density is really just dependent upon mass. So which balloon has the larger mass? We already said it, it was argon. All right, so which balloon has larger density? Again, it would be argon. Both balloons have the same volume again, and then therefore mass is the driving factor for density, and which one has the larger density, the larger mass? Argon. All right. What are the values for X and Y? So the next 2 questions deal with combustion reactions. So for this one, this is just the law of conservation of mass. Same thing, we have to make sure we have the same number of elements on each side. So here, we're going to look at CO2 is where we get our carbon from. There are 3 of them. That means X is 3. And then if we look at H, hydrogen shows up here. There are 2 hydrogens, though, in water. So 4 times 2 means there are 8 hydrogens here, which means back here we had to have 8 hydrogens. And there we go. So the formula would be C3H8, which is propane. Okay, so in this problem, we're talking about combustion analysis, common AP Chem question, right, from this section here. So some compound had carbon, hydrogen, and nitrogen inside, and it made 12.923 grams of CO2, 6.608 grams of water, and then the nitrogen was treated with hydrogen gas, and 2.501 grams of ammonia were produced. The complete combustion of 11.014 grams of the compound needed 10.573 grams of oxygen. So what's the empirical formula? So first off, we don't need this for this problem, and we don't need this. So while true and probably useful at some point, not for this question. So let's not even bother with that. So all we're going to do is take each amount we're given. So we have 12.293 grams of CO2. And we want to find out, okay, from this 12.923 grams of CO2, how many moles of just carbon were there? So how do we do that? We first divide it by its molar mass. So this is moles of CO2. Okay. And then if we look at the compound, for every 1 mole of CO2, we get just 1 mole of carbon. We're going to do the same thing again. So we have 6.608 grams of water. Water has a molar mass of 18 grams for 1 mole of water. All right. And then for 1 mole of water, we don't get 1 hydrogen, we get 2. So we have 2 moles of H. All right. And then last but not least, 2.501 grams of nitrogen, I'm sorry, of NH3. The molar mass of ammonia is 17 grams, gives you 1 mole of NH3. And then this is just mole ratio. For every 1 mole of NH3, there's also 1 mole of N. And now we can just solve each one. So the first one is 12.923 divided by 44. This is 0.294. For the next one, 0.734. And then the very last one, 0.147. And then, just like before, it's a mole ratio problem. So this is moles of carbon, this is moles of hydrogen, this is moles of nitrogen. So we're going to find out what the mole ratio is. So find the smallest number, it's 0.147. Divide everything by 0.147. And if it doesn't come out evenly, just round it to the nearest whole number. It should come out basically even or very close to like a nice whole number. So this is 2, right? This works to 5, it's like 4.99. And this is 1. So now what's our formula? It's C2H5N. That is the empirical formula. Okay, so stoichiometry. So you guys were definitely learned stoichiometry last year, how we convert from one item to the next. Crucial part of chemistry, still necessary all the time in AP Chem. And we always treat AP Chem problems. If you're not sure, it's usually a limiting reactant problem, unless it's abundantly clear in the problem that you're going to have something in excess. Usually they'll use the word, you have something in excess. So we look at this one. So 200 grams of zinc nitrate are dissolved in a solution, and 85 grams of aluminum are added. How much zinc is produced? So we're just going to do this problem kind of twice. So if we have 200 grams of zinc nitrate, all right, so the molar mass of zinc nitrate is 183. When you're finding the molar mass, you should always use the actual numbers on the periodic table. I know I was rounding before. I don't really care if you round in my class. On the AP test itself, definitely use the whole numbers. A lot of times, though, in this class, if you need to find a molar mass, they usually give it to you. They don't really want you to have to spend time doing something that's considered rudimentary chemistry. That doesn't really test the knowledge of what they want you to know in class. Okay. So that is for a mole of the zinc nitrate. Okay. And if we look at our equation, for every 3 moles of zinc nitrate, we get 3 moles of zinc. So now we can just solve. So 200 divided by 183, right, 1.09. All right, that's moles of zinc. Okay, so that's how much the zinc nitrate produced of zinc. Now we'll do the same thing with the aluminum. All right, so 85 grams of aluminum. Aluminum has a molar mass of 27 grams, is 1 mole. According to the equation, for every 2 moles of aluminum, we get 3 moles of zinc. We could solve this, we'll solve it anyway. We can already kind of tell, or hopefully you can look by now, that aluminum is going to be massively in excess. It's going to be a much larger number than what we got from the zinc, which means the zinc is our limiting reactant. Yeah, this can produce 4.72 moles of zinc. So the limiting reactant is always the one that produces the least amount. So how much zinc do we make? We made 1.09 moles of zinc. If we multiplied it by its molar mass, we would find out how many grams of zinc we made. For this problem, all right, we're going to try to do this without a calculator. We're going to see if we can do this just by hand, okay? So we have 0.22 liters of propane, and we have 3.2 grams of oxygen, and they are combined in this combustion reaction that we have listed right here, right? Oh. And we want to find out how much water is produced. We're going to look at the limiting reactant, and then we want to, at the end, find out how much more of the limiting reactant we need for it to be equal or not the limiting reactant anymore. Okay. So we have 0.22 liters of propane, and we're at STP, so that means for every 22.4 liters, there's a mole of propane. And then in the equation, for every 1 mole of propane, we get 4 moles of water. Okay. All right, so how do we solve for this? Well, let's just look. 0.22 divided by 22.4 is roughly 0.01, and 0.01 times 4 is 0.04. Okay. So that's how many moles of water we get from propane. So down here, 3.2 grams of oxygen. The molar mass of oxygen is 32 grams for a mole. And in this equation, it takes 5 moles of O2 to make 4 moles of water. Okay, so 3.2 divided by 32 is 0.1. Okay? And then rather than trying to divide by 5 and multiply by 4, 4/5 is 0.8. Okay, so 0.8 times 0.1 is 0.08. All right, and that is moles of water. So who's our limiting reactant? So first of all, how many moles of water produced? 0.04 moles of water, because that's all we've got. What element is limiting reactant? It's water. It's propane, because it made the least amount of water. And then how much more would we need? Well, in order for oxygen to not be in excess, or in order for, I should say, for propane to not be the limiting reactant, we would need to make 0.08 moles of water. Well, we only made 0.04 moles, so we would need to make twice as much water. So that means we would need to start with twice as much propane. And since we measured propane in liters, we would need 0.44 liters of propane, or a little more than 0.44 liters of propane. So it would not be the limiting reactant. All right. All right, and then last is molarity. All right, so molarity is concentration in chemistry, and it's one of the many units for concentration, but in AP Chem, it's the only one we're going to worry about. The only one we deal with is molarity, which is moles per liter, and sometimes we'll deal with millimolar, which is thousandths of a mole. We'll get to that later in the year. We talk about acids and solubilities much later on, but for now, molarity. So how many grams of solute in 0.250 liters of 0.15 moles of potassium bromide? So molarity equals moles per volume. So if we just set it up like this, 0.15 times 0.25, and that's 0.0375 moles of potassium bromide. All right, then we got to find out, hey, what's the molar mass of potassium bromide? And the answer is, I have no idea off the top of my head. So let's find out. Potassium bromide, molar mass, 119, works for me. Okay. So 0.0375 times 119. 4.46. Grams of potassium bromide. Right. Again, molarity is moles over liters. We didn't have moles, we solved for moles, and we just multiplied the moles by the molar mass. Okay. You have a stock solution. That means it's the concentrated solution of 14.8 molar ammonia. How many milliliters of the solution should you dilute to make 100 milliliters of 0.250 molar NH3? Okay, so we're going to show you how to do this in two ways. First way is the long way, and then I'll show you the shortcut. So the long way, we actually want to start with this. Our final solution is going to have a concentration of 0.250, and it's going to have a volume of 0.1 liters. 100 mils is 0.1 liters. So in that solution, how many moles of ammonia do we need to produce that solution? Well, if we multiply 0.1 times 0.25, that's going to get us 0.0250 moles of ammonia. So that's how much ammonia we need. Okay. Well, where are we going to get this ammonia from? Where we're going to get it from this stock solution. So we want to find out how much volume do we need. So for 14.8 molar, that's going to be 0.0250 moles. That's how much moles you need to pull out of this. So we're going to need how much volume. So we're looking for this. So we flip these around. We get 0.0250 divided by 14.8. And that gets us 0.0016. How many sig figs we got? 3, 1.69. All right, that's liters, but it says mils, so multiply this by 1,000, move the decimal 4 places over, or 3 places over. 1, 2, 3. You need 1.69 milliliters. Very small amount to make that solution. So that's the first way. Again, notice everything revolves around the mole, right? Here is the other way. And if this formula isn't given to you for some reason, I can't remember if they provide this one for you guys on the AP test or not, but this is when we program into our calculators. As this is a great formula, shows up potentially and really easy to use. So this formula is the dilution formula. M1V1 equals M2V2. Molarity of the initial, all right, times how much volume you need of the initial equals molarity of the final times the volume of the final. Nice thing about this formula, units don't matter as long as they stay consistent. So in this question, here's what we know. The initial concentration is 14.8, okay? We're trying to find out the volume. We don't know how much volume we need from it, right? And then we know our final solution has a volume of 100 mils and a concentration of 0.250, right? Solve for V1. So 100 times 0.25 divided by 14.8, right? And let you know you get 1.69. And since we left this in mils, our answer is automatically in mils. All right, and here's the last question, acids and bases. So we'll get to whole units on this. Don't you worry, guys. But for this one, we don't need to worry about any knowledge of acids and bases. So hydrochloric acid is a strong acid, and it reacts with sodium hydroxide, which is a strong base. In an acid-base reaction, the equivalence point occurs when the moles of the acid are equal to the moles of the base. True. So it took in a reaction, it took 12.5 milliliters of hydrochloric acid to reach the equivalence point with 10 grams of sodium hydroxide. What is the concentration of HCl? Right. So to solve for this, right, let's think about it. Here's what we want to know. We want to find out the molarity of HCl. Okay, that's the question. To find out molarity, we need moles over volume. Well, we already know the volume. It's 0.0125. 12.5 mils in liters is 0.0125. But we don't know the moles of HCl. Right? That's what we don't know. However, we don't know moles of HCl, but we can get there from moles of NaOH. So that's what we're going to do. We have 10 grams of sodium hydroxide. The mass of sodium hydroxide is 40 grams. Okay. According to the ratio, for every 1 mole of sodium hydroxide, we get 1 mole of HCl. So that's 0.25 moles of HCl. Now we can plug that right up there. So 0.25 divided by and I'm sorry, you hear my daughter crying in the background. She just woke up. Divided by 0.0125. Okay. I just thought I typed something in wrong into my calculator, did not. 20 molar. That's concentrated. All right. I'll put out some more questions later on that you guys will have to complete. I hope this video helps. If you have any questions about any of the problems that we did, please don't hesitate to let me know. All right. Good luck. Enjoy the rest of your summer. I'm looking forward to meeting you guys all come September, if not sooner than that, via reminds and stuff. And if it would be useful, feel free, guys, to let me know. If you guys want to have like a Zoom session over the summer as a recap and work, just let me know. All right. See you guys later. Enjoy the rest of your day or whatever time you're watching this is. That's the beauty of the internet.